Hello everyone, I'm Chi-Shen. I come from Department of Engineering and System Science, National Tsinghua University. My supervisor is Xin-Yi Tiffany Chen. The topic I want to present is DFT insight into the design of catalysts for oxygen reduction reaction applied to fuel cells. There are two parts. The first part is a work cooperated with City University of Hong Kong and published in JMCA this paper. And the second part is a work cooperated with National University of Singapore. Do you feel hotter and hotter these years? There are many greenhouse gases. Carbon dioxide is one of them. When we want to get electricity, we burn coals or fossil fuels. However, it will simultaneously produce a large amount of carbon dioxide. Yet, we have another choice, fuel cells. Simply put hydrogen and oxygen inside the fuel cells. Then we can get electricity. Isn't it easy? Nevertheless, at the cathode, the reaction is called oxygen reduction reaction, namely ORR, is too slow, which will restrict the overall reaction rate. Scientists used platinum or palladium as catalysts previously because they have good ORR performance, but they are expensive. These years, scientists came up with another idea called core shell nanoparticles. You can imagine there are two balls, a small ball which consists of cheaper elements like cobalt or nickel, and it is inside a larger ball which is composed of noble elements like palladium. And then we can decorate PT3 clusters onto it. Scientists' experimental groups reveals that this core shell nanoparticle structure has the good ORR performance while lowering the cost. Here's the methodology part. In a simulation, we build many models, and we need to use the formation energy formula to check which models are more stable. The smaller value means that the models are more stable. And we also use the absorption energy of oxygen atom, this formula, to calculate the absorption energy of oxygen atom. The smaller value means the stronger bonding between the oxygen atom and our catalysts. Here's the parameter settings. We use PBE as our exchange correlation function. The software we use is VASP. We use ideal single-state models to mimic the nanoparticles. And there are two types of models. One is absorption models, and the other is the replacement models. We calculate all of them for formation energies, and we find that the replacement models, their formation energies are lower than the absorption models, which means the replacement models, they are more stable than absorption models. So we use the replacement models in the following simulation. We change the combination of layers in our catalysts and build these models. And we use two descriptors for oxygen reduction reaction. The first is the absorption energy of oxygen atom, and the second is D-band center. We can see in the upper figure, this is a volcano plot from Noskov et al. We can see that among all the elements, platinum is the closest to the volcano peak, which means it has the best ORR performance among all the elements. So we set platinum as our benchmark. We hope the ORR performance of our catalysts can be similar to that of platinum. We can see the lower figure. It is also a volcano plot. And the number 3 here is the platinum 111 surface. We can see that platinum 111 is also the closest to the volcano peak. So we want the D-band center of our models closer to platinum. Here is a result 1, absorption site effect. We can see that in a 1-layer platinum 5-layer cobalt and 1-layer platinum 5-layer nickel, the absorption energy of oxygen atom layer values are closer to that of platinum, minus 0.82. And also we can see that we absorb the oxygen atom, the red one, the red ones are oxygen atoms and the orange ones are the platinum atoms. We absorb the oxygen atom to 3 Pt atoms, 2 platinum atoms, 1 platinum atom, and no platinum atom. And we find that when we absorb the oxygen atom in the Pt3 hollow site, in this site, the values are larger. The absorption energy of oxygen atom are larger. That means they are weaker than others. So we think that platinum 3 hollow site is the best absorption site. Second, we also calculate the D-band center for all our models. We can see these two models. They are in a star shape, which means n equals to 1. N equals to 1, we see that they refer to 1-layer platinum, 5-layer cobalt, and 1-layer platinum, 5-layer nickel, and they are 4 field symboled. That means they are in the platinum 3 hollow site on each surface. Their positions, we can see that the x-axis is the D-band center, and the y-axis is the oxygen absorption energy. These two models, their positions are closer to platinum, which means that they will have the better ORR performance among all the models. Third, we also calculate the oxygen dissociation barrier. We can see a schematic figure here. The oxygen molecules come to our catalysts and dissociate into the oxygen atoms. So the lower for the oxygen dissociation barrier, that means the easier for the oxygen molecules to dissociate into oxygen atoms. And we can see the figures on the right. The models we built, they have the lower oxygen dissociation barrier than pure platinum in the figures. That means our models has better ORR performance than pure platinum. Here is a conclusion for the first part. We investigated into the absorption sites, D-band center, and oxygen dissociation barrier, and find that indeed the core shell nanoparticles structure can enhance the ORR performance while lowering the cost. We appreciate the help from the professors, postdocs, and seniors. Also, the simulation resources from NCHC and the financial support from most. This is the end of the first part. It seems that we have done a great job so far and published it on JMCA. However, we are still thinking some questions. In fact, the experimental groups, they synthesized the catalysts in the form of nanoparticles. But the models we used in simulation previously are ideal single-state models. They cannot present the grain boundaries, and we think that the atoms on the grain boundaries might have a higher ORR activity. So we start to think, maybe we should build the nanoparticle models. But which size to choose and which shape to choose? According to Tangdong Liu et al., they built out these 6 shape of nanoparticle models for simulations. Then we start to think which to choose and how to build them. Also, the absorption sites. Take truncated octahedron models as an example. There are 3 special sites: edge sites, corner sites, and turret sites. Which site should we absorb the oxygen atoms and the hydroxide group? So there are many questions for us still need to solve. Here is the second part of my report. First, we need to determine the shape. We choose the octahedron model and the sphere model as the preliminary models and check which one to build. After testing, we find that the octahedron model, their formation energies are lower than the sphere models. So we choose octahedron models as our preliminary models. Also, we build out many sizes for octahedrons and calculate their formation energies. We find that as our atom numbers get larger, then the formation energies get lower. Considering the precision and the simulation resources in our lab, we determined to choose the 146 platinum octahedron models as our preliminary models in the following simulation. In the 146 platinum octahedron models, there are 8 facets. Each facets are equilibrium. No, they are equivalent. So we only need to investigate into one facet. In each facet, there are these replacement sites and these absorption sites. So there are many combinations, but many of them are repeated. After deleted the repeating ones, we have these 7 replacement models and these 5 absorption models. And here's the ongoing work part. We will absorb oxygen atoms and hydroxide groups onto our models, and we want to build the nanoparticle reaction diagram look like this. This is the diagram from Norskov et al. We also want to build out the nanoparticle volcano plot. This volcano plot is also from Norskov et al. They use the ideal single step models to build out this volcano plot. But we think maybe nanoparticle volcano plot might look a little bit different from this plot. So we want to try to build out the nanoparticle volcano plots. Also, we will calculate the D-band center and the oxygen dissociation barriers in the future. In this work, we appreciate the help from Professor Sergey in National University of Singapore. Also, the simulation resources from NCHC and the financial support from MOST and the Ministry of Education New Southern Pilot Overseas Internship Program. Thank you for your attention.